Okay, student, good afternoon to you all. Am I audible to you all clearly?
Yes, sir.
Okay, so I'm just uh, putting this screen for you. Is this screen visible to you all?
Yes,
Yes,
sir.
sir.
Okay. So in the last class, actually, we discussed about um, obviously biological techniques, actually how this work, uh, how can we prepare the nanoparticles using the biological techniques or using the um, environmental just friendly the way out, how to reduce the chemicals using the yeast or using the fungi or using the bacteria or using the virus, or it can be done using the plant extracts. And thereafter we discussed one technique for preparation of nanoparticles, and that is we discussed studied solid gel techniques. And at the same time we discussed one techniques for the thin films. So for thin films, we discussed a study about the spray pyrolysis. So these two techniques we discussed in details yesterday. Today we are going to discuss thin films. For thin films, the technique is LB technique. The technique is said to be the LB technique, and its name is based on the scientist name Langmuir Blodgett film deposition techniques. Actually, this equipment looks like in this way. The equipment is actually in this way you can see. And your substrate is somewhere going to be hanging from here to downside. And this tray is actually filled with water. And on water, actually, you are going to put your sample, and that depends on the sample nature. Either it is going to spread over your this liquid, and most of the times it is going to use the water only. So either it is going to spread over this water or the liquid surface, or it is going to make the droplet. So it depends on, actually it depends on the nature of your materials. Basically, the nature of materials is to be named by the micelles here. Actually, the in LB technique, this micelle is wording is for the this micelle is nothing rather than the aggregation of aggregation of aggregation of uh, this nanoparticles. So you can see here that in thin films you are going to prepare, then many quantum dots are going to be ready in order to prepare a thin films. So what actually happening here, these missiles have actually head and tail. So it depends on that which types of molecules you are having. It is hydrophobic, sorry, this is hydrophilic or the hydrophobic. As its name suggests, if it is attracting towards the water, then it is said to be the hydrophilic. And if it is to be repulsive nature, or it is hating the water, then those material is said to be the hydrophobic materials. But here we are talking about the group, so that which is going to uh, is it going to head towards this water, or it is going to tell with the water. It depends on the situation, that the your materials are going to spread over the liquid, or your materials are going to be make the droplet over the surface of the liquid. So if it is going to form in this way, what you are looking here, if its a tail is here and head is outside, then it is said to be the micelle structure. It is said to be the micelle structure. While if the pattern is going to be off, then it is said to be the reverse micelle structure. So what's actually happening, if you say the it's the way out, or you can say names here, that if you go, you put the water in wire aisle, then you are going to get this way. And if you are going to put the aisle in water surface, you are going to get this surface. So this is said to be the micelle structure, and this is said to be the reverse micelle structure. So in both way it can be formed, and otherwise if you are going to make the bilayer, then you can use in this way, that bilayer is going to form in this way out, in this pattern, that bilayer you are going to be formed. If one micelle structures and one reverse micelle structure you are going to prepare, then you are going to get the bilayer in this way out. Otherwise your bilayer is going to happen one this, thereafter other is going to happen in this way only, and in that way your multi-layer is going to be happen. So ultimately, if you see, if the dispersion medium is aqueous solvent, if dispersion medium is aqueous solvent, several molecules aggregate in such a manner that hydrophobic radicals form a core, that is inner element, while hydrophilic groups form the surface layer of the micelles. So you see, it depends on the your materials is hydrophobic or hydrophilic. Accordingly, the micelle structures are going to develop over the water surface. And if the dispersion medium is an organic liquid, molecules a micelle may have a reverse orientation when the core made up of polar group and hydrophobic radicals are turned inwards. So it is said to be the reverse micelle structure. So what actually you are looking here in this Langmuir-Blodgett techniques, you see the Langmuir-Blodgett through trough must be installed in a clean dust-free environment. So the trough where actually you are going to put the water, that is said to be the trough. Water, mercury, glycerol are most commonly used subphase. Standard solutions of the materials of our interest were prepared in highly volatile water, insoluble organic solvents such as chloroform, benzene, etc. What actually I am talking so far, that where we are going to put our materials, that is volatile water surface are there. Why they are saying volatile? Since once your materials are going to be adopted over the substrate, these water are going to be just evaporated. So what's actually happening here, if you see the monolayer spreading, how monolayer spreading is going to happen. So the known quantity of solution was spread at the air water interface, and sufficient time was given to evaporate the solvent, and then the molecules remains at the air water interface haphazardly. So what's actually happening, your this trough is there where you have just it is full of water, actually it is a full of water. Then what you are going to do, your materials, what your precursors you are having, those precursors you are going to be put drop by drop over this solution of this liquid solutions. Then what is going to happen, these drops are going to be here, since once it is going to be somewhere in between the upper side, it will be the air atmosphere, the normal atmosphere, and inside it is the water atmosphere. At the same time, you do have the facility, if you do have facility in your this LB techniques, if you do have facility, then you can manage this environment also. You can put that outer atmosphere is argon atmosphere and the lower atmosphere is of the liquid atmosphere. So this is going to be two phase. Above side is of air and downside is to be liquid. So what is going to happen, once you are going to put the drop of this your materials, then it takes time in order to get settled down, that it is going to be hang somewhere between the liquid and the air phase. So there are two phases exist. One is the liquid phase, other is the air phase. In between your this micelles, what you say here, they are going to be individual micelles are going to be stand in this way, or it may be the reverse micelle or reverse way also. So what is going to happen, this is the way how your materials are going to be spreading over the water solution, And if you see here, in this case, if you see carefully, then what you are going to find that you do have here, when the molecules are first spread on the water surface, what we see in just earlier slide, that when the molecules are first spread on the water surface, they are loosely packed. They are loosely packed and form a so-called gas phase. So just you see, when it is just you have put the your materials over the water, then they are going to spreading over the water surface, but they are not that much strongly packed. But what is to be happening, increasing the surface pressure by compressing the barrier cause a transition to a liquid phase. So what actually you do have a barrier here. Just you see, it is a barrier here. In this barrier, what you are doing actually, here this is having a very long space for your missiles, what is to be here. But once you are just pushing it in this directions, once you are pushing in this direction and you are here, at that time what is going to happen, your materials are going to actually they are going to little dip into this liquid solution. And once it is you are increasing more it, then what is going to happen, they are going to come completely close one to others. So this coming closer to one to others, they are going to set to be the solid formation. So it is said to be the solid form of your missiles, of your materials, where it is said to be the liquid forms and it is said to be the gaseous form. So increasing the surface pressure by compressing the barrier cause as a transition to a liquid phase. Further increasing in pressure bring about a last compressibility change that is associated to the solid phase. So what we are saying, that this is the solid phase. So this is said to be the solid phase. And once you are going to increase more pressure thereafter, it is going to be collapsed in this way. So further decrease in area per molecule causes collapse of the monolayer. Since this is a one layer only, so it is said to be the collapse of monolayer. So it is going to form your solid phase here. Thereafter collapse is going to occur. So actually these things you cannot see in your material sample during this synthesis. Only what you are going to get, you are going to get a plot between this, what you are getting here, surface pressure where molecular area, you are going to get a, means with respect to pressure and area, you are going to get a graph. With respect to pressure and area, you are going to get a graph, and based on the graph you are going to define that your materials have actually formed or not. So for that reason, actually you are looking that your graph is somewhere you will get in this way. So once you are getting this straight vertical lines, you are going to say that your materials have already comes into the solid phase. So what actually happening here, this is not the end. Actually, once you are going to pushing this barrier at this end, then at the same times here one substrate is going to be hanging here in a directions that it is going to be whatever surface, once it is will be down, then what is going to happen, once it is to be down, then these materials are going to wrap. Actually these materials are going to, once actually suppose these are the missiles, say suppose these are the missiles here, these are the missiles here in this way, then once you are going to drop a here, say for I am saying this, this is the substrate, this is the substrate in this way, this is the substrate here. Once it is going to appear here, you are pushing it down. Once you are going to pushing it down, what will happen, it is going to form this missiles are going to form over this substrate as a one layer. then what you are going to do, you are taking it out, you are holding it for 2 minutes, at least 2 to 3 minutes, thereafter you are again going to dip into in the same solution. Then again the same way missiles are going to be formed here, and again when you are going to dip it, then again dip is going to start actually water always being the volatile. Here since you are preparing the material, then you are saying volatile water. If you are preparing your materials in some liquid, then they are said to be the aprotic solvent or volatile solvent. So it depends on you, you set the nomenclature. So water is always volatile. Yes. What you want to ask actually?
Sir, actually, I am here. Volatile water means water will be disappear in that material. Yes, sir.
No, huh, obviously once you see actually.
It means is there any external? It means any external temperature it will be volatile, or due to the material it will be automatically volatile.
Automatically volatile. No heat treatment is here.
Okay, sir. No pressure, no temperature, nothing. It will be
No,
automatic.
actually pressure, temperature and air atmosphere, it can be add-on attachment. Actually, these are the add-on attachment. Add-on attachment means, since it can be done based on your requirements, but this LB techniques, these attachments are not there. Only this trough is there. That trough is there where you can put the solvents here, over which you want to just spreading your material samples. And once you are dipping your substrate here, those materials are going to get attached over this your substrate. That's enough, nothing else. And once it has been just attached with the substrate, you take it out and put it in a general, normally means in the same atmosphere. If there is no gases, nothing is there in the air atmosphere, put it for 2 to 3 minutes. In 2 to 3 minutes, the whatever the volatile solvents are there along with this substrate and the materials, those volatile solvents are going to be disappear. Yes.
Okay, sir.
Okay. So this is the one technique actually is used. Actually, all techniques are not going to be used for the same materials. It depends on the what actually materials you are preparing. For those materials, you are going to choose the techniques accordingly. So this is the one techniques of the thin films apart from the spray pyrolysis. The next one is again the thin films. Again the thin films preparation. And in this thin film preparation, if you see, this is the very easy handling actually techniques, where actually it's mostly used for preparation of polymer nanocomposites. So most of the times polymer nanocomposites are going to be formed using this solution cast techniques. So in this techniques, actually it is time taking, but it is a very easy techniques. Actually, in polymer nanocomposites, normally there are 3 types of elements, or you can say precursors, are present. One precursor is said to be the polymer itself. It is said to be the host here in this case. Other is said to be the salt. Salt is actually, you see, these are the always ionic salt, where they are going to get dissociated in the ions, maybe cations and as well as anions. And some reinforcing materials are going to be taken, reinforcing in terms of the voltage, in terms of the temperature, in terms of the you can say mechanical. So in that forms, you are going to use some third actually precursors here. So ultimately, all 3 is going to prepare a polymer composites. And nanocomposites is going to form once you are going to take this reinforcing materials of dimension of nanometer. So this is the introduction about the polymer nanocomposites. So what actually you are doing here, whatever the host materials you are any polymer you are taking, that host polymer is going to dissolve. It is going to dissolve in somewhere the those volatile solvents, volatile, or you can say aprotic. Aprotic it is used to say solvent. In those solvents, it is going to be just prepare. Actually, it is going to dissolve. These polymers are going to dissolve in those types of solvents, and once it is to be dissolved properly, thereafter you are going to add the ionic salt over there. Once ionic salt is going to be added in this polymer solution, then what is going to happen? These ions are also going to be get dissociated. So after dissociations, cation and anions are going to interact with this polymer as their as based on their requirements, as you are looking so far, and how reactions are going to take place. Then you are going to add on the filler there. So it is going to take around you say 25 to 30 hours. Here the same phenomenon, in order to get dissolved salt in this polymer solution, it is again 20 to 25 hours minimum it is going to take. So you see 2 days here, 2 days here. Thereafter, you are going to add on this filler or what I said, the third reinforcing materials here. So that reinforcing materials after addition, again you have to go for 20 to 25 hours here. So ultimately it is about 6 days. And in all cases, when you have dissolved, you put on steering for 25 to 30 hours. Again, here steering for 20 to 25 hours. The same steering takes place here 25 to 30 hours. Thereafter, it is going to be casted over, casting is going to be done over the Petri or any glass slide or over any flat surface where you are going to get do the suppose you have the glass substrate, you are going to just pour over this glass slides, and a film is going to appear here. You are going to left it for roughly 10 to 15 days in the vacuum, actually vacuum desiccator. Normally it is going to put in the vacuum desiccator where no atmosphere is there. Then the solvents are going to be evaporated completely, and you are going to get a freestanding polymer nanocomposite films. So this is the solution cast techniques. It is a very easy technique, but time taking, and you have to look, you have to patience, and you have to wait for complete drying of these films, and your films are going to, once it is going to be dried, then it is going to left the Petri dish or the glass slide where it has been deposited. So you are going to get the freestanding, not the film over the substrate. Here you are getting the freestanding thin films. So I hope you got this also. So let me, if you are going to take with examples, then you can see here addition of a specified amount of polymer to solvent and kept for steering for homogeneous mixing. In the solution cast techniques, the solvent must be free from water content and should be a universal solvent which can dissolve both salt and polymer. The process of preparation of film is lengthy and long. It may take a long time, 10 to 15 days, to get a complete dry film, and also expensive in chemical use. Organic solvents such as DMF, acetonitrile, tetrahydrofuran, and polypropylene carbonate, ethylene carbonate, or diethylene carbonate, whatever the solvents are, you can be used, since all having the boiling temperature of around the 40 to 80 degrees centigrade. So it is a good method for preparing ionic salt and proton conducting system, but fail to metal salt or the bigger ions. So I think you got this solution cast techniques in a very brief. If someone have any doubts, you please ask.
Hello, sir. Sir, in case this is the long process now, when it will be time taken, these inside the material taking some disorderness, we get output will be wrong method. It will be possible to getting wrong output, sir.
No, actually, it's having a time taking, but nowhere actually, if you are giving so much time, certainly you are going to get a very good quality films here. You see what actually you are doing here, you are putting the long time here for 20 to 25 days, sorry, 20 to 25 hours here. It is, you are ensuring that whatever the polymers you are having, they are going to completely dissolved in the solvents. Once it is dissolved, then you see you are adding the secondary elements here, and you are again ensuring that this polymer and salt are going to interact completely. If their interactions are going to be completely, or it is going to be proper interactions, then they are going to again become the transparent, or completely mixing is going to be done. Then after, you will go for the third addition of ternary compounds, or you can say ternary filler or clays. Then that is said to be the reinforcing materials. Then again you are ensuring the same things. Once you are having the complete solution, then those solutions are going to, because of the polymers, they are going to come little bit in the little bit in the jelly nature, but you can maintain that viscosity based on the solvent concentrations. If solvent concentration is strong, you can reduce the viscosity. So what is going to happen? Once a petri dish you are going to take in, flat surface petri dish you are going to be taken, and once you are going to pour this solution over here, and you ensure that what much solution, how much solution we are going to put over here, by which it is going to spread uniformly over the whole surface. Once it is going to uniformly put over the whole surface, then their thickness is going to be controlled, and it will be automatically done because of the viscosity is not that much, viscosity is poor, then it is going to completely cover the surface. And as it is petri dish, complete this petri dish, covered petri dish, you are going to put into a vacuum, this vacuum desiccator. Once it is going to put into the vacuum desiccator, here the silica gels are there, extra silica gels are there, which are going to absorb all the solvents what is to be present here. And because vacuum is here, so no other contaminants are going to happen here. So you are going to get a very good film here, and freestanding films where nowhere the interactions of the substrate involved, since it is going to left this once it is going to dry it is going to left this petri dish. Yes.
Sir, in case here we are mentioned less than some time 20 to 25 hours like that. If our if we are taking these techniques is the less than that time, or we are considered above the time, it will be not affected, na?
No, less than time you are not going to completely dissolve materials. Maybe their aggregates are present, means maybe polymers are not completely dissolved, maybe salts are not completely dissolved. They are going to make aggregates there, uniform films you are not going to get. And the long time is more than that, you can go through since you are doing the better mixing. Yes.
Okay, sir, I got it.
Okay. So this is about the solution cast techniques. Somewhere in the same directions, actually, whatever we discussed, the same way everything is exactly the same. Solution is going to be formed up to the third points. Up to the third points, steering is done here. Whatever we are just putting the solution here in the petri dish or the glass slide here. Rather here what we are doing, we are just putting those materials over a dish. Actually here a dish is there, and that dish actually having a, just once you are going to put the your materials here, and because it's having the rotation, because of the rotations, it will offer them a centrifugal force, and because of the centrifugal force, the materials are going to be spread over whole the disc, where at the disc actually you do have the substrate. Over the substrate it is going to be formed uniformly. So you are going to get films, thin films here over a substrate of circular disc, and once it is going to thereafter you again transfer this into the vacuum desiccator. That substrate is going to transfer into the vacuum desiccators, and again you are going to get the freestanding thin films here also. Yes. Is it okay?
Sir, can I ask one thing?
May I know your name? I think Bira.
Yeah, sir.
It's okay. Yeah, Bira, please.
Sir, here we are putting something, a solution in that glass plate. We are giving to angular velocity. These solution will be going out of this glass plate also, not possible. If it's possible, sir.
Obviously, this actually each and every technique is not that just you are coming and you are just using. You can use it as a you can see, it means randomly you cannot use it. Just you have come and you are going to do this thing. You required actually practice. Actually, it's all the techniques are, you say, practical hands. Actually, once you are not going to well versed with these techniques, you are not going to handle it properly. So you have to see your seniors how they are doing the things. Thereafter, you have to go through how jelly your liquids are there, how much the speed is there, all things you have to control based on use of the experiment. Once you are going to use it, then and then you can realize that how much velocity, angular velocity I have to give there, how much jelly liquids I have to put over the substrate. Those things you have to optimize yourself. Yes, Vida.
Okay, okay, sir. Sir,
Okay.
one more thing. When we are using this thing, precursor word we are using. Sir, precursor means that will be two substances. We will make the one substance like that, sir. Precursor.
No, not precursors means only, just you remember, precursors means in order to prepare what actually you want. Suppose you want to deposit a, say for I am just roughly taking that iron oxide. You want to deposit or make the iron oxide nanoparticles. And say far you don't have, either you do have the iron, say far I am saying iron acetate you have, iron acetate you have, iron nitrate you have, or iron, once I am making this, then you can make it accordingly these things. I am not writing this twice or thrice, what you are E plus 2, then it is 2 plus 3, this it is 3, accordingly it is. So you are going to use these types of materials since you don't have the iron oxide. So extracting from here to here. So in order to getting this, you are going to take this or this, since both are the precursors. So you are using this precursors or you are using this precursors. So it may be one, or in order to prepare this in the case of, suppose if iron oxide is not there, I am saying that you are preparing lead titanate, TiO3. So for this, you see, you have to go for the precursors of, say for I am looking the lead nitrate. I may look for the titanium. Titanium, I am looking the titanium acetate, and oxygen automatically coming from the water. So I am taking 3 precursors in order to prepare the lead titanate. I am thinking that you are getting the points.
Yes, sir. Yes, sir. Yes,
Okay.
sir. Sir,
So,
in case I am using solar cells like methyl ammonium lead chloride like that. Here 3 precursor I am using. Yes, sir. Like this. Same example.
again, just you tell me what you are preparing.
Methyl ammonium lead iodide.
Lead iodide.
I mean 4 precursors.
Obviously, for this, taking something from where you are getting this carbon, somewhere from where you are getting nitrogen, somewhere you are getting the lead, somewhere this hydrogen is going to automatically get from the water, or somewhere this hydrogen you can get from the water, or something you are going to prepare. For iodine, you have to go for somewhere where iodine is present. So in order to getting complete this compound, what are the different materials you required in order to prepare this complete compound? All those materials are said to be the precursors. Yes.
Okay, sir. Okay, sir. Thank you, sir.
Okay. So next is actually, this is the next technique, that is said to be the hot press techniques. You say in the technique wise, if you are looking the synthesis, if it is to be much more, then I'm going to leave here. If you want that, it's okay. I can move ahead. The students. Since techniques listening is actually and getting grasp of all these things, it's not that much easy. So if you are thinking that it's too much, then I can leave here. Other, if you are saying, then one more techniques I may discuss right now. The students.
Yes, sir. No problem.
Okay. So what's actually here, you see the hard press techniques. Actually in the techniques, it seems that it is very, actually by name, you may not have heard the name, but all techniques are very, actually, if you are going to use to with the technique, then you are going to realize it is nothing, it's a very easy process. But once you are going to use it, in the beginning, it may looks very hard. Actually, this is the whole description about how hard press techniques work. But I'm telling again in the same way that first polymer you have prepared, second you have just added salt here. Just I'm putting this precursors. You may take any precursors here. I have just taking here the reinforcing materials here. All 3 materials solution is there. And so far I am just taking here that this is a you can say a, you do have the this sample container actually where sample is going to be taken, that is here, and in that sample container it may have this pellet size. So what you are doing, the complete solutions you are going to put over these 2 points. Then what will happen, thereafter you are going to cover it again, and after covering it you are pressing it using the hydraulic press. You are pressing it, maybe the pressure you may give based on the your actually requirements. And temperature control means here the furnace is going to install here itself. So what will happen, once you are going to press it, the materials are going to press in it inside, and temperature is given here. Then what will happen, whatever solvents are there, they are going to get evaporated, and complete solid pellet you are going to get from here. So it is said to be the hot press techniques. It's a very simple and you are going to get it, but always in order to not having any contaminant, you wash it properly. You do it means once you have wash it, you make sure nothing is here present. And these whatever the roller, or you can say whatever cylinders are here, they you make the cleaning of all these things where you are putting. Once it is going to covered, thereafter outside environment is not going to affect it. Rather whatever the so you this is actually this is showing about that it both are the points where actually thermocouples are there, and they are going to heat it properly and homogeneously. So you can put it in pellet size, you can put it cylindrical way, you can make the materials your of maybe the prismatic types, whatever the types you want. Accordingly you just prepare, accordingly your sample holders are there, you put the samples there, and you are going to get the solid materials of that requires actually what materials you require. Those nanomaterials are going to be formed here. It is said to be the hard press techniques. Yes.
Sir, means temperature and pressure are both increasing.
Yes, actually it's increasing, but it depends on what materials actually you are taking so far. If you are looking the polymer here, if it is PO, you don't have required for the temperature. Even since its temperature at after 65 to 80 degrees centigrade, it will be melt. So you require here the solution is there. You put it around 50 to 60 degrees centigrade if PO is present. But if you do have the ceramic materials, then you have to go for 500 to 600 degrees centigrade. Yes. And pressure accordingly. Is it okay? You may go through the line by line. I may read this thing also, by which you may get more clear. In place of the traditional solution cast techniques, hard press techniques is novel techniques due to its advantages such as quick method, low cost, solvent free, and may be used for the dense materials. One advantage of this method is that a lot of alkali solvents, salts and metallic particles can be complexed with various polymer hosts. The equipment consists of weighing cylinder, heating chamber, basement, and temperature controller. A dry powder mixture of optimized amount of polymer, salt, and filler is grounded thoroughly at room temperature for 1 to 2 hours in agate mortar pestle. The physical blended mixture is heated slowly near the melting point of the polymer in heating chamber, and slurry obtained is then sandwiched under the pressure between two stainless steel blocks. The sample is then pressed with a pressure controlled by a weighing cylinder. It results in a hot slurry of different compositions of the polymer, salt, and filler, which is separated from stainless steel blocks for further use. The hard press technique is a complicated for lithium ion due to reactive nature of lithium salts in the atmosphere and unique processing conditions as required in the case of lithium dependent materials. Yes, students, is it
In
okay?
this process, nanomaterials
Sir,
or
what is agate
nanotubes
pastel
Huh?
and
are
pastel?
Oh, actually, I think you have not gone in the laboratory. If you have gone in the laboratory, there is actually, in order to make the size reductions, you require, say, pestle and mortar. So that requires in order to putting it the in the making your materials in a smaller size. If it is having little bigger size, you are going to make it the smaller size using just uh, rubbing those materials with the help of mortar. Yes, and pestle.
so nanomaterials or nano thin films are prepared in this process.
In this case, actually, once you are going to, it depends on what actually you are here putting. Since it is freestanding, it may be the tablet, it may be the film, it may be anything, but it is of the nanomaterials only. Reason why it is going to dried and pressed, but it is going to prepare the nanomaterials since they are coming from the bottom up approach. Yes, so it can be thin, or it will be the pellet. So it films category you may put them. Is it okay?
Yes, sir.
Thereafter, next is tape casting techniques. Again, it is related to the what we discussed just earlier. In that case, we were actually using the just roughly we are pouring over the petri dish. We are pouring the solution over here, and it is going to form a uniform thickness. But if you don't have the control over the viscosity, then what is to be happening? Actually, I don't have here the solution, but you see here the master blade is here in with the help of master blade. Actually, what is going to happen, they are having the vacuum gauge by which you are going to put as a squeeze, actually like a squeeze is here, the blade is here, they are going to just you are going to slide it from one end to the other ends, and you are going to get a controlled thickness film. So whatever is there, you are thin films are going to prepare automatically. Here you are with the help of squeezer, master blade is there. It is going to prepare the thin films here. So if tape casting techniques, if someone is interested, they may visit my lab and they can see how it is going to happen there. So it's nothing here. For thickness, screw gauge is there, and here the motor controlled, or you can use yourself. You are going to just pull it from one side to other sides, and a complete thickness means control thickness films are going to appear of the order of micrometer. So this is said to be the tape casting techniques. Is it okay? Or I have to read here? So if you see, I can
Yes, sir.
read for you. In this method, stoichiometric amount of host polymer salts are dissolved in a suitable solvent such as acetonitrile, DMF, whatever we said in the earlier slide, that solvents in a beaker, and solution is stirred for 10 to 12 hours. So time is varying actually, whatever we are looking here depends on the what polymer and what salt you are taking. Now dispersion of nanofiller in different weight percent with respect to host polymer is done in the polymer salt complex in the desired ratio. And again stirring is done for the same time as above. Now the resulting viscous solution is transferred on the preheated hot plate for small time duration. This preheated hot plate may be heated, may not be heated. It depends on your requirements. Cast by a tape caster with further drying slowly at room temperature. Thus, we obtain the freestanding conductive polymer nanocomposite films of the desired thickness. The whole process is done in an inert atmosphere such as glove box. It can be, this is again in on your requirements. A stainless steel container with slurry is connected to a gas steel chamber. The slurry flow rates is controlled by the gas pressure, and amount of slurry at a scraper is kept constant. When a carrier is passed through a slurry at a fixed rate, there is a slit between the edges of the scraper and the carrier. When the slurry on the carrier with the thickness of the slit is dried, a membrane is obtained and rolled into the package. The slit can be adjusted to prepare membrane with varied thickness. Both thickness and width of the films can be easily controlled by these techniques and suitable for the production at industrial scale. I think you got the points if you have gone through point by point. Or anyone have any query? So the same way, everything is in the same way, but here only the transfer of slurry at a preheated hot plate, that is preconditional, and casting by tape caster, then it is said to be the tape caster, or it is said to be the master blade techniques. Master blade techniques. So either it is master blade or the tape caster, whatever you say, it is going to prepare this material. Thereafter, you go for the slow drying at room temperature in the vacuum desiccator of the glove box, and you are going to get the freestanding polymer nanocomposite films. So up to here, the next techniques we are going to discuss in the next class. It's okay to you all?
Yes, sir.
Okay. So let us go for the attendance. Alok, Anjana,
Present, sir.
Asgar, Atul, Brahmanand,
Present, sir.
Abdul, Diya,
Present, sir.
Deepshita, Kalpana, Kiran,
Present, sir.
Kuldeep,
Present, sir.
Magan,
Present, sir.
Murli,
Mostly present, sir.
Namcha,
Present, sir.
Naveen,
Present, sir.
Rohit, Roshan, Sagar, Sarang,
Present, sir.
Simple, Saurabh, Suprabha, Harshita,
Present, sir.
Ritan,
Present, sir.
Markant,
Present, sir.
Markant,
Present, sir.
Hitesh, Shweta,
Present, sir.
Soumya, Veera,
Present, sir.
Rahul,
Present, sir.
Vinod,
Present, sir.
Yogesh,
Present, sir.
Nitya,
Present, sir.
Virendra. Virendra is there? Virendra is present? No. Okay. So good luck to you all.